Okay. Hi everyone, welcome to today's class. Today we are still on youtube.com/@bestsciencebrain, and today we're going to take a look at A-level chemistry, advanced level chemistry. The topic of the board is examination of formula of organic compounds by quantitative combustion analysis. So this topic is organic chemistry, and it is suitable for students that are in high institutions, tertiary institutions, year 1, first year and second year, those doing science courses like chemistry, pharmacy, medicine, microbiology, biochemistry. So this is for you. So today, we'll first of all start by defining combustion. What is combustion? Combustion is the reaction whereby a substance burns in oxygen. So the reaction of a substance with oxygen is called combustion. It's also known as oxidation using oxygen. So, but today our focus will be combustion of organic compounds. And as we know, organic compounds involve millions of compounds. That is, compounds that contain carbon and hydrogen and perhaps some other elements. So, in the combustion, we're going to start with combustion of hydrocarbons. We're going to start with the first class of a compound called hydrocarbons. Hydrocarbons, as we say in the first video we had on this formula of compounds, hydrocarbons are compounds that contain carbon and hydrogen only. The general equation for combustion of hydrocarbons is on the board. CSHY plus S plus Y over 4 oxygen, giving us SCO2 plus Y over 2 H2O. So this is the general equation for combustion of all hydrocarbons. Where CSHY stands for the hydrocarbon, S is the number of carbon atoms, YY is the number of hydrogen atoms. So to balance the combustion equation of any hydrocarbon, be it an alkane, be it an alkene, be it an alkyne or aromatic, you can use this general formula. For instance, if I use methane, CH4, in methane, S is 1, whereas Y is 4. Going to this formula and input the values CH4 plus S being 1, S being 1, Y being 4 over 4, O2, giving us 1 for S, CO2, Y is 4, 4 over 2 H2O. If you solve out, 4 into 4 gives us 1, while CH4 plus 2O2, that is 1 plus 1, equal to CO2, but the one here is not relevant, doesn't make any difference. So divide, we have 2H2O. So this is the combustion equation or the oxidation of methane. Let's see whether we got it right. Carbon atom is 1, we have carbon 1 atom here, 1 over there. Hydrogen is 4 atoms here, 2 times 2, 4. Oxygen is 2 times 2, that is 4. And this side, 2 here, then 2 times 1, 2. So 2 plus 2 giving us 4. So see the equation is balanced, obeying the law of conservation of matter. Okay, if I take another instance, apart from using methane as an example, I can use another example from another homologous series. Perhaps let me use C3H6. This compound is called propene, an alkene. So in this one, S is 3, H is 6, Y is 6. So putting the values here, C3H6 plus 3 for S plus 6 over 4, that is 6 for Y, oxygen giving us 3 CO2, 3 for S, then Y is 6 over 2 H2O. When we solve out, this will give us 3 over 2, or 3 over 2 is 1.5. C3H6 plus 3 plus 1.5 gives us 4.5 oxygen, then 3 CO2, 2 into 6 is 3 H2O. Look at this equation, is balanced, yes? Carbon is 3 atoms here and 3 atoms over there. Hydrogen is 6 atoms here, 3 times 2 is 6. Oxygen is 4.5 times 2, 9, Over there, 3 times 2 is 6, 3 times 1, 3. 6 plus 3 will give us 9. If you don't wish to balance using decimal values, you want to convert the decimal value to a whole number. You multiply the number of moles all through by, you used to multiply the number of moles in front of every substance. We now have 2C3S6 plus 2 times 1 here is 2, 2 times 4.5 is 9, 2, 2 times 3 is 6, then 2 times 3 again is also 6. You have the full equation. So if you look at this, 2 times 3 is 6 of carbon atom is 6 here. Well, we'll have 6 carbon atoms over there. Hydrogen atom is 2 times 6 is 12. Then 6 times 2 12. Oxygen 9 times 2 is 18. Oxygen 6 times 2 is 12. Then 6 times 1 6. So 6 over here plus 2 are giving us 18. It is still a balanced equation. So having done that, you can look at the board again and understand the concept involved in writing combustion equations of a hydrocarbon. All hydrocarbons obey this equation CSHY, where S and Y stand for the number of carbon atoms. Like in propene, S is 3, Y is 6. Then S plus Y over 4, oxygen, SCO2 plus Y over 2, water. So if I use propene for instance, and now replace, this is CS, this is propene here, replace S with 3, replace Y with 6, 6 over 4, that gives you 1.5. Then over there, replace S with 3, then replace Y with 6, 6 over 2. You solve out, you're going to have C3H6, 3 plus 1.5 is 4.5, then 3 CO2, 2 into 6 is 3. Then open the bracket, you have this equation balance. So we're going to go into the calculations involving combustion of hydrocarbons. How to derive molecular formula and empirical formula by using combustion quantitative analysis. Okay, now we have this question on the board, on the whiteboard. Combustion of 6.51 milligram of an organic compound gave 20.47 milligram of carbon dioxide and 8.36 milligram of water. The molecular weight of the compound is 84. Calculate A, the percentage composition, B, the molecular formula of the compound. So this is an example of illustration of combustion compound, how to obtain empirical and molecular formula by using combustion analysis. So how do we go about this? To solve it, write mass of compound. Mass of organic compound that was combusted is 6.51 milligram, milligram. Okay? Then we'll divide the board into 2. We're solving for A, percentage composition. So we're going to look for percentage of carbon. We all know that organic compounds normally contain carbon and hydrogen. You may still have other elements. If you look at this question, they did not tell us the kind of organic compound we'll have. It could be a hydrocarbon, it could still contain carbon, hydrogen, and other elements. But let's start with carbon and hydrogen. At the end of the calculation of the piece of hydrogen and carbon, if there are any other elements, we'll find out. I will tell you how to find out whether there is a third element or a fourth element. So, having done that, then the mass of carbon dioxide, mass of CO2 produced from the combustion is 20.47 milligram. Having done that, we'll find the relative molecular mass of CO2. You know how to get it? Carbon is 12, or I give it to you in bracket. Carbon is 12, the mass of carbon is 12, hydrogen is there, oxygen is 16, multiplied by 2 atoms. That gives us 44. Then here, mass of carbon in CO2, mass of carbon in 1 molecule of CO2. Now you then put it in CO2. So there is only 1 atom of carbon in CO2, and the mass is 12, which is the mass of carbon. They will now find mass of carbon in 20.47 milligram of CO2. Mass of carbon present in this mass of CO2 produced. You use a mole ratio of carbon multiplied by this 20 mass of the carbon 4 oxide. Mole ratio of carbon times the mass of carbon 4 oxide produced. That will give us the mass of carbon inside this quantity. So what the mole ratio of carbon? Mole ratio of carbon is nothing but the mass of carbon, the mass of carbon all over relative molecular mass of carbon 4 oxide. That is 12 over 44 times 20.47 milligram. So having done that, having done this, we obtain 5.58 milligram of carbon present in 20.47 gram of carbon 4 oxide. We'll do the same thing for hydrogen. We'll now find hydrogen is found in water. So mass of water produced in the equation, mass of water produced is equivalent to 8.36 milligram. So relative molecular mass of water will now become 2 times 1, the atoms of hydrogen is 1, and there are 2 atoms here, plus 16 for oxygen, that will give us 18. Now the same thing we did here. We now do mass of find mass of hydrogen in 1 molecule of water. That going to give us mass of hydrogen in 8.36 milligram of water. So mass of hydrogen in this water produced will now be mole ratio of hydrogen times the mass of water produced, which is 8.36 milligram. The same format we apply for carbon. So we're going to have the mole ratio of carbon of hydrogen going to be 2 times 1, because hydrogen is 2 atoms in water, and the atoms of hydrogen is 1, so 2 times 1 all over the molar mass of water, which is 18, multiplied by 8.36 milligram. And that will give us 0.926 milligram of hydrogen. So we have to understand the process involved. The mass of CO2 produced 20.47. After I've gotten that, find the molecular mass of CO2 by adding the atomic mass of carbon to oxygen. You have 44. Then find the mass of carbon in CO2. Mass of carbon in CO2, there's only 1 atom of carbon in CO2, that becomes 12 grams, that's the mass of carbon. The mass of carbon in 20.47 grams of CO2 produced will now become the mole ratio of carbon times the mass of CO2 produced. How to find mole ratio, which is mass of the compound all over molecular mass. Mass of carbon, which is 12, all over the molar mass of CO2, 44 times the mass of CO2 produced. That will give us 5.58 milligram of carbon. Then going to water, the same thing applies here. Mass of water produced 8.36 milligram. We find the molecular mass of water, which is 18, that is 2 times 1 plus 16. 1 is the mass of hydrogen, also is 16. Then here I forgot, mass of hydrogen, yes, in water, it should be 2 times 1. There are 2 atoms of hydrogen in water, so that gives us 2 grams of hydrogen inside water. Then we now find the mass of hydrogen in 8.36 grams of water. We now have the mole ratio of hydrogen times the mass of water produced. 2 over 18 times 8.36 will now give us 0.926 milligram of hydrogen. We are yet to arrive at the percentage of carbon and hydrogen. So we now go to the percentage of carbon and then the percentage of hydrogen. So to find the percentage of carbon, you can click this side. You have a video on the board. If you want to put something down, you can pause your video and then put it down. Then let's find the percentage of carbon. The percentage of carbon will now become mass of carbon all over mass of compound times 100 over 1. Remember the mass of carbon we obtained is 5.58. Now I have 5.58 all over the mass of the compound is 6.51. The mass of compound 6.51 times 100 over 1. When we do this, we get 85.7%. And that's the percentage of carbon according to question 1. Also, to find the percentage of hydrogen, we apply similar process of hydrogen in the compound. We now have percentage of hydrogen will now be equal to mass of hydrogen all over mass of compound times 100 over 1. From our calculation, we got hydrogen mass as 0.926. And the mass of the compound remains the same, 6.51 times 100 over 1. We're going to get 14.3%. So you have obtained the percentage of carbon and that of hydrogen. You have to ask yourself, is there any other element which could likely be oxygen that should be present in the compound that you did not get the percentage, because they did not tell you that it's a hydrocarbon. If it's a hydrocarbon, we are sure that it is carbohydrate that is present. But how to find out whether there are any elements present? How to know that if there's any other element present? We add these percentages, 8.57 and 14.3. If you add it, it's going to give you, it gives you 100%. That means there are no other elements remaining. But if it does not give you 100%, then you have to add the two of them and subtract from 100. Then you now get maybe the percentage of oxygen. So if you add this, we're going to have 100%. Perfect 100%. That means there's no other element remaining. And that means this compound given to us here is a hydrocarbon. So the carbon percentage is 5.7. While hydrogen is 14.3%. Okay, we're going to question B, which says find the molecular formula of the compound. But before we go to molecular formula, we'll first of all find the empirical formula. Before you move to molecular formula, you must know the empirical. So to find the empirical formula, we'll have to leave the percentage that we obtained from question A, carbon 85.7, hydrogen 14.3. The first step in getting empirical formula is dividing these percentages by the atomic masses. So divide with the atomic masses, or the RAM of each element, as we explained in our first video. When you divide this, we have 7.14, 14.3. The next thing you do, divide again with a smaller value. Out of the two ratios you obtain, divide the smaller value. The smaller value here is 7.14. 7.14 is the smaller, so divide both of them by 7.14 and approximate your answer to the nearest whole number. That gives us 1. This one gives us approximately 2. That means the empirical formula of the compound is now C. We're going to give 1 to carbon, there's already 1 here, and 2 to hydrogen. So this is the empirical formula of the compound. Now we're moving to molecular formula. To get molecular formula, we'll have to put empirical formula in bracket, multiply by integer n, and make it equal to the molar mass or the molecular weight of the compound, which is given to us as 84. What 84? So you now have CH2, which is the empirical formula, multiply by n equal to 84. We now find the molecular weight of the empirical formula. Carbon is 12, atomic mass of carbon is 12 in bracket here. Hydrogen is 2 times 1, then n equal to 84. So we now have 14n equal to 84. Our n becomes 84 over 14. That gives us a perfect number, which is 6. Now, we'll now go to this expression CH2 bracket n and replace n with 6 and open up the bracket. CH2 bracket 6. We'll have 1 carbon times 6 gives us 6 carbon atoms. 2 times 6 gives us 12. So this is the molecular formula of the compound, and this compound can be called hexene. So with this, we are done with this calculation. We'll take the next example on this topic. Keep on watching and always subscribe. Subscribe to this YouTube channel so you can get more videos. Okay, we now have another problem on the board. but a pretty difficult one, or more difficult than the former one we solved. We have 0.2835 gram of organic compound containing carbon, hydrogen, and oxygen and chlorine, 4 elements. Give on oxidation 0.2637 gram of carbon dioxide and 0.809 gram of water. In the halogen estimation, 0.1891 gram of the refined compound produce 0.2835 gram of silver-1 chloride. Calculate number 1 the percentage of the different elements. 2 the empirical formula. 3 we'll ask for the molecular formula with this formation. Okay, to solve this problem, we're going to start find the percentage of the elements one after the other. We're going to start with carbon first. The same way we solved the other one, but the former example, write the mass of the organic compound. Obviously, this compound not hydrocarbon because I've seen 4 elements that, apart from here, I see oxygen and chlorine. So mass of the compound is 0.2835 gram. So we want to find the percentage of carbon in the compound. So mass of the compound is 0.2835 gram. Then mass of carbon dioxide produced in the equation or in the combustion is 0.2637 gram. Then, as we did before, find the molecular mass of CO2. When you calculate it, carbon is 12 from the atomic mass value, also is 16 multiplied by 2, that will give us 44. Then find the mass of carbon in carbon dioxide. There's only one atom of carbon in carbon dioxide, and the weight of carbon is 12. The mass of carbon is 12 grams. We will now find mass of carbon in 0.263 gram of carbon dioxide. How do we do that? We take the mole ratio of carbon multiplied by the mass of carbon dioxide, which is 0.2637 gram. And mole ratio, as I said before, is obtained by using the mass of the element, which is 12, all over the molecular mass of the CO2, which is 44, times 0.2637 gram. So when we do that, we're going to have, by calculator, 0.0719 gram of carbon in the compound. So we'll now go ahead to find the percentage of carbon in this compound. So to find the percentage of carbon, we'll now use percentage of carbon, what the mass of carbon, all over mass of compound, multiplied by 100 over 1. So mass of carbon we obtain is 0.0719. Mass of the compound 0.2835 multiplied by 100. So when we solve this, we'll get 25.4% of carbon present in the compound. So carbon is giving us 25.4%. So we'll now go to the percentage of the next element, which is hydrogen in water. The next element is hydrogen. So to find the percentage of hydrogen, the same procedure. Say percentage of hydrogen in the compound. Now find mass of water produced, because hydrogen is found inside water, of course, which is 0.809 gram. Then relative molecular mass of water will give us 2 times 1 for hydrogen plus 16 for oxygen. You have the mass in the bracket, that giving us 18. The mass of hydrogen in 1 molecule of water. The atom of hydrogen is 1, but there are 2 atoms of hydrogen, that becomes 2 times 1, giving us 2 grams of hydrogen. We now find mass of hydrogen in 0.809 gram of water that it was produced. That gives us mole ratio of hydrogen times 0.80, which is the mass of water. And the mole ratio of hydrogen is going to be the mass of hydrogen in the water, which is 2, all over the molecular mass of water, which is 18, then multiply by 0.809, which is the mass of water. When we solve this, we'll now find the mass of water inside this compound using calculator. The mass of water is going to be mass of hydrogen is going to be 0.899. Mass of hydrogen, please, not water. 0.089 of hydrogen inside this mass of water. Now, to find the percentage of hydrogen in the compound produced, when I say percentage of hydrogen in the compound, that becomes mass of hydrogen all over mass of compound multiplied by 100/1. So mass of hydrogen is this 0.0899 all over the mass of the organic compound, which is 0.2835 multiplied by 100/1. When we solve this, we get 31.7%. So hydrogen is 31.7% in the compound. So let's confirm answer with calculator. It will give us at 1.7%. That's right. So, having done that, we go to the next element, which is we may not easily find oxygen because there are no data given to us about oxygen. So we go to chlorine first. So now we go to percentage of chlorine in the compound. So how do we do that of chlorine in the compound? We are told from the information to say that in the halogen, estimation 0.1891 gram of the compound, pure refined means pure compound, produce 0.255 of silver chloride. So now say 0.1891 gram of compound produce 0.2835 gram of silver chloride, AgCl. Therefore, mind you, the amount of compound that was produced, that was combusted with this. Therefore, 0.2835 gram of the compound we then produce 0.2835 multiplied by 0.2835 all over 0.1891 by proportion. So we now have, using calculator, we now have 0.425 grams of silver chloride that will be produced by 0.2835 of the compound that was subjected to combustion. So we are still going on, we're not yet with that of chlorine. So this is this. We now have 0.425 grams of silver chloride produced by burning 0.2835 of the compound given to us in the equation. Now, having done that, we now continue. Now, the mass of silver chloride calculated is 0.425 grams. We now move over to estimation of chlorine percentage. We find the relative molecular mass of silver chloride. That gives us silver is 108 in bracket, chlorine is 5.5, giving us 143.5. The mass of chlorine in silver chloride in 1 mole of silver chloride, there is only 1 atom, and that is 35.5 grams. Then we now find mass of chlorine present in 0.425 grams of silver chloride. Mass of chlorine inside this mass, that becomes mole ratio of chlorine times 0.425 grams. So when we do that, we now have the mole ratio is nothing but the atomic mass of the element, or the mass of the element, all over the relative molecular mass. That becomes 35.5 all over 143.5 times the molecular mass, the mass of chlorine all over the molecular mass of silver chloride times 0.425. Solving this with calculator, we now going to have 0.105 gram of chlorine in the compound. We now find the percentage of chlorine. Okay? So of chlorine, we now have percentage of chlorine will now become mass of chlorine all over mass of compound multiplied by 100 over 1. So mass of chlorine we estimated is 0.105, that is 0.105. The mass of the compound is 0.2835 times 100 over 1. Solving it, the calculator will get 37.0% of chlorine. So chlorine is 37.0%. Then they didn't give us any data about oxygen in this question, but they told us that there is oxygen in the compound. So how do we now find the percentage of oxygen? As I told you in the previous video, the formula of compounds 1, the first video I made, I said that if you add the percentage of elements in a compound, all of them together, you add all of them together, you must get 100%. So you add all the elements together, you get 100%. So since we have gotten this remaining oxygen, we'll now make oxygen the solid formula. So percentage of oxygen will now become 100 minus the sum of that of carbon plus hydrogen plus percentage of chlorine. That gives us 100 minus carbon is 5.4 up there, hydrogen is at 1.7, and chlorine is 37%. So when we sum all these, we now get oxygen percentage as 5.9% of oxygen in the compound. So having done that, we have answered number 1, which is the percentage of the different elements in the given compound. Then going to number 2, number 2 says we should find the empirical formula. So write out oxygen here as 5.9%. So it becomes easier for us to solve. So to find the empirical formula, we follow the normal process. Since we know the percentage composition of the elements, we leave the percentages of the elements. Okay, what the is negative here. So 5.4, at 1.7, 37, and then 5.9. Divide each percentage by the relative atomic element. This is 12. I give around 2.12. Why is going to be hydrogen 1 at 1.7. Divided by 16 for oxygen, divided by 35.5. Using the calculator to estimate that of oxygen, that also give us 0.369, while that of chlorine will give us 1.04. Having done that, we now divide this value with the smallest ratio. Out of the 4 of them, the smallest is 0.369. So 0.369, 0.369, 0.369, 0.369. They give us approximately 6, give us approximately 89, 1, and then 3. Let's confirm calculator. Okay, that hydrogen is 86, not 89. So the ratio 6 is to 86 is to 1 is to 3. So the empirical formula of the compound now becomes C6H86 for hydrogen, O 1 oxygen, and then Cl3. So this is the empirical formula of the compound being demanded. So we go to number 3 question III. We say that if the vapor density of the compound is 141.75, what is the molecular formula? So we'll go ahead to solve. First of all, we have to convert this vapor density to relative molecular mass. And you know in chemistry, from gas laws, molecular mass is 2 times vapor density. That becomes 2 times 141.75. That gives us 282. Let's confirm. 282.5. Okay, 283.5. Okay. Now having done that, we now move to get the molecular formula. We now have empirical formula times n. We give us the relative molecular mass. So the empirical formula determined as C8 C6 H86 got OCl3. Yeah, that was what. Then multiply by n equal to 283.5. So how to find the molar mass of the empirical formula? So carbon is 12, 2 times, that is 6 times 12. The amount of carbon is 12 multiplied by 6. Hydrogen, the amount of hydrogen is 1, 86 times 1. Oxygen is 16. While chlorine, be 1 atom only. While chlorine is at 5.5. The amount of chlorine, then multiply by 3 because of the presence of 3 atoms here. Then n equal to 283.5. We now solve what we have in the bracket. Solving what we have in the bracket, we're going to have a calculator. We're going to have 280.5. So when you solve, you have 280.5 n. Upon the n outside, that gives us 283.5. Making n the subject, n becomes 283.5 all over 280.5. That gives us approximately 1 whole number. So having done that, we now go back to the empirical formula, which is C6H86 OCl3 multiplied by n, that expression followed by n. We will now replace n by 1. To replace n with 1, we have C6H86OCl3. Replace n with 1 and open the bracket. 1 has no effect. You open the bracket, you have C6H86OCl3. This is still the molecular formula. So the molecular and empirical formula are equal to each other since n is equal to 1. So we'll go to the next question.